Books have been written about this thing, you know. You can find a formula. You can derive a formula for the ith term. But yeah, I'll just say that that's something you can do, and I would assign in an upper level math class as a homework problem. Probably not appropriate for here at the moment. Yeah. Listen, guys, so all of these limits that I'm writing have something in common. Every last one of them so far. They are examples of something where if we were to take the limit as n goes to infinity, like, oh, no, we were having such a nice discussion. Why are you doing this? A sub n. And usually we use sub n, not sub I, for a sequence. I don't know why. I usually talk about I to start with, but eventually I'll shift back to n. Limit as n goes to infinity of a sub n is equal to L. What this means, definition, if and only if, for each epsilon greater than 0, there exists m in the natural numbers such that n greater than or equal to m implies the absolute value of a sub n minus L is less than epsilon. Otherwise, if no such L, no such L exists in the reals, of course, then we say that the limit we say the limit as n goes to infinity of a sub n diverges or just that a sub n diverges. And there's no ambiguity in saying that here because, you know, you talk about a function, right? F of x. And I talk about the limit of f of x. What kind of limit am I talking about if x is a continuous variable? What kind of limit am I talking about? You shouldn't know, right? I mean, how many different kinds of limits? You can think about limits approaching 2, right? Limits approaching 3 from the left, from the right. Limiting approaching infinity, a limit approaching minus infinity. Pick any real number. We can consider the limit of it provided it's in the interior of the domain, provided it's a limit point for f. So for a real valued function of a real variable, there's all sorts of different limits to consider. But for a sequence, there's just one kind, right? The only limit to consider for a sequence is what? The limit as n goes to infinity. And so, by the way, we also get to say this. We'll say a sub n goes to L as n goes to infinity is yet another way we can denote this, which is super nice because we don't have to write limit. We can use arrows, right? If we use this sentence. So all of my examples, 1, 2, 3, 4, these were all divergent sequences, right? Because look at what happened with the nth term. Did it go to something? No, right? It gets. I mean, this we don't even know what happens. Like we're blinded by ignorance. We don't know what my entire name is. Maybe it repeats. Maybe it's James, 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 James. Maybe it's James and then it's John and then it's I don't know. Who knows what happens to the sequence? We don't have enough information. We have no idea what happens past what I wrote, really, right? This one, it gets larger and larger and larger, so this one's not going to converge. right? Common sense. The initial one, so let's write down some examples. 5. Where am I? Example. Oh, I started renumbering, didn't I? It's my sequence example 5. So let's just do a bunch of easy examples. Just knock them out. How about this? N, the limit as n goes to infinity of, say, n squared plus 3n minus 7. So the top one is infinity, right? The next one, right? How did you know that? Right, so what are you assuming, by the way, you guys? Limit as n goes to infinity, or how about this? Different notation. Inverse tangent of n goes to blank as n goes to infinity. Complete the sentence for me. Yeah, pi halves. How about e to the minus n goes to blank as n goes to infinity? I'll make it more exciting. 3. 3 plus e to the minus n goes to 3, right. How about this? N e to the minus n goes to I've got another picture to draw over here, by the way, guys. Getting back to it. How about this? It is an indeterminate form. Let's think about this. So if we have f of x equals to x e to the minus x, right? For x in the reals, then f of n is equal to a sub n for all n in the natural numbers. So this is a continuous real valued function which matches the sequence at whole numbers, right? And I can calculate the limit as x goes to infinity of x e to the minus x. What is it? It's x over e to the x, which then has type infinity over infinity. Which is going to give me 0. So why do I introduce the x variable? What's that?
How do we know that for all n it's an element of the natural? So how do we know that? Or is that just what
Well, if I plug in n into here, I get back n e to the minus n. So it matches this. I'm calling this a sub n. It's ambiguous until I write that. So this is my sequence. This is a function. They have the same formula when n is a natural number. But x e to the minus x is defined for like square root of 2. F of square root of 2 is square root of 2 e to the minus square root of 2. A sub square root of minus 2 is not defined. This is only for n being a natural number.
So that was like negative 2. So it would be negative 2 to squared? I don't know.
Let me draw a picture. So what's going on here, for a convergent sequence, right? We could have all kinds of crazy stuff happening. But after some, here's the limiting value, let's say. So, the sequence can be doing all kinds of crazy stuff, but at some point, these are supposed to be equally spaced dots. I'm not very good at this. We just add a bunch of them so we can't tell that I'm horrible at my spacing. The point is, you can pick. Suppose I'm looking at this epsilon band. So here we're looking at L plus epsilon. Here we're looking at L minus epsilon. Geometrically, this m I have in the definition, it's, for this one, it says 1, 2, 3, 4, 5, 6, 7, 8. Apparently, if I put my m equal to 9, if I have n greater than or equal to 9, that puts me out here. And out there, see this right here, this is the distance between the sequence and the limiting value. So I want that distance to be less than epsilon. So this is what it means for the sequence to converge. It means that if I go out far enough, I can squeeze the values of the sequence into some little band, right? But this is the same thing that's meant by if you have the limit as x goes to infinity and f of x equals to L. What's that mean? That means that for each epsilon greater than 0, there exists some m in the real numbers such that x greater than or equal to m implies that the value of f of x minus L is less than epsilon. Let me draw the picture for this. That picture looks more like this. That's not my best picture. Try that again. So maybe the limiting value is this or something, right? So if I pick my epsilon band to be like this, I can choose my m to be something like that. And beyond there, the function's getting squeezed into that little band, and that means that the limit is L. So you see that if I have this, then what I can do is I can say, oh, okay, well then if I just take the function and restrict it to natural numbers, whatever happens, if it just, natural numbers, then you see that there's some kind of link between the continuous extension of the sequence and the function. Whatever limit you find for this is also shared by that. And what that means is we can use L'Hopital's rule for sequences, provided we're understanding what we're doing. Do we understand what we're doing? I'm even willing, guys, and this is my... So I have... here's language we can use. We could say limit as n goes to infinity of n e to the minus n, right? Here's what I'll say. I'll say that this is equal to the limit as n goes to infinity of n over e to the n, right? And then I'll say by L'Hopital's rule, type infinity over infinity, this is the limit as n goes to infinity of 1 over e to the n. Now, can you tell me why that should be concerning to you? What does L'Hopital's rule do? You're differentiating, right? How do you differentiate a sequence? What's the derivative of the Fibonacci sequence? We have not defined that. So there's a sleight of hand going on here. And to be completely transparent with you, what I should say here is extending n continuously. So in past years, I would insist, in fact, I probably should still insist for you guys, that if you're going to apply L'Hopital's rule to a sequence, I just want a little comment in the side that says extending n continuously. You can abbreviate. You could, like, extending n continuously. I'd be cool with that. But I just want some note, because technically speaking, we shouldn't use L'Hopital's rule for sequences, right? We're using an extension theorem whenever we do that. All right. So my larger point is every single limit we looked at infinity, there's a corresponding result for sequences, which is why we did L'Hopital's rule right before chapter 9. That's why. So anyway, I'll see you guys tomorrow. Oh man, I went 2 minutes over. I'm so sorry. Shame on me. We should take a whole day off sometime, right?